So moving on with our quadratic unit, we are going to take a look at how we can use our quadratic functions with some modeling. So our first exercise we're going to take a look at, we have an object is fired upwards with an initial velocity of 112 feet per second. Its height in feet above the ground as a function of time in seconds it was fired is given by this equation. So first question we have to do is think about at what height was the object fired. So a different way to say this is, what is your initial value? A different way to say this is, what is your y-intercept? So if we're going to make a y-intercept, we want to make your x value equal to 0, or in this case, it would be our t value. So in our formula, we're just going to substitute in a 0. So I have negative 16 times 0 squared plus 112 times 0. Okay? And if we simplify this, anything times 0 is 0, which is going to tell us the height it was initially fired at is going to be 0 feet. So a general curve of this equation, if we were to sketch this, a couple of things that we know. Number one, because this value here is a negative 16t squared, that negative tells us it should be opening down. It's a parabola that opens down. I know my initial start of this graph is going to be at 0. So I know that that's got to be there. If I were to label my axis, I could say this has to be h of t and this has to be t. Okay, good axes would have arrows, so we're going to go back and put that on there. And in general, I know it's opening down. So if I were to take my parabola and graph it, general graph is going to look like this. Now we'll go back and we'll label some important points after we solve these next few questions. Okay, so we're going to algebraically find the time that the rocket reaches its greatest height, maximum height. So in other words, I'm trying to find that value right there. Okay, and if I'm thinking about it on that graph, this maximum height is going to be our turning point. So if that's our turning point, we had a formula to find our turning point, negative b over 2a. So if I want to find that value, so it's a negative b over 2a, that's our equation. All right, using our information from our given equation, our b value is 112. So I have a negative 112 divided by 2 times our a value, and our a value is a negative 16. Okay, so if I simplify this, this is going to give me about 3.5. And our label here would be seconds. Remember, t being time is seconds. Okay, so that would be like our x value. So I know I could label over here 3.5. Now what I also need to do is find the y value that it corresponds with. So if I go back to our given equation, and in place of the x value, I plug in that 3.5, I have a negative 16 times 3.5 squared, and then plus 112 times 3.5. And that you can plug all into your calculator just like that as a string. And when you do and you simplify, you get 196. If we were to think our label, that should be feet. So I could label our turning point over here at 3.5 comma.
At this time, any thoughts?
196. And if I were to think about this from maybe just a question standpoint, we could say here at 3.5 seconds, the max height of 196 feet would be reached. So that's how we could interpret that question. Okay. And lastly, it's asking us to algebraically determine the time when the rocket reaches the ground. We want to label this on our graph. So if the rocket is going to reach the ground, I want to think, well, the height has to be 0. So if our height is 0, that's like saying set your equation equal to 0. And then from there, I could solve for T, because again, keep in mind it's saying determine the time when it's going to reach the ground. Okay, so for something like this, I could factor out a GCF. And my GCF on this, I could pull out a negative 16T, and that would leave me with T minus 7. Okay, setting each of these equal to 0 to solve for T, I can find T is going to be 0, which we know because that was our initial start. And then if I set this equal to 0, I can find T is equal to 7, which that is telling us that would be a total of 7 seconds that it would take for the rocket to reach the ground. So if we were to label that on our graph, over here, this coordinate, I could say it would be 7, 0. It's 7 seconds it hits the ground, which is 0 feet. Okay, taking a look at our next one. So we have the Crazy Caramel Corn Company has determined that the percentage of kernels that pop, rise, and then fall as the temperature of the oil the kernels are cooked in increases. It's modeled by this formula. It says P is representing the percent of kernels that pop. T represents the temperature of the oil in degrees Fahrenheit. So P is a percent, T is temperature. Okay, so we have to algebraically determine the temperature at which the highest percentage of kernels pop. So now let's think about that. Highest percentage of kernels. So that again, that would be like our maximum point on this graph. And again, we know it's a maximum because if I look at that negative sign, I know that this would be opening down. So if it's going to open down, I know in general, I'm thinking it's going to look something like this, where I should have some sort of a maximum on our graph. Okay, so keeping that in mind, I'm trying to find your turning point, which again, it has that formula negative B over 2A. So our B value is 2.8, so I have a negative 2.8 over 2A, and our A value is a negative 1 over 250. Okay, so use your fraction template for both of these things on your calculator. When you do, and I'm going to ask you to try this on your own, make sure that you're getting this. This value should be 350 degrees Fahrenheit. Okay, so they wanted to know the temperature at which the highest percentage of kernels would pop. And then it says also determine the percent of kernels. Keep in mind, the P of your formula is your percent. So kind of like we did on the last one. Once we know what the value is here, I want to plug that back into the formula and solve for P. So I have a negative 1 over 250 times, we're going to plug in our value that we found, 350 squared, plus 2.8 times 350 minus 394. So again, plug that all into your calculator. That can all go in as a string. I'd use your fraction template for the negative 1 over 250. Double check and make sure you're doing this correctly, but that's going to be about a 96% pop rate. That's pretty good. Okay, so it says using our calculator, we're going to sketch a curve below for P being greater than or equal to 0, and we're going to label our window. Okay, so I have already graphed it, and this is what it looks like. Notice I changed the window, so it took a little bit to get it into the window. You can play around with that until you get a good window. And I'm going to take this and put this over here. Okay, so we have our axes. This is going to be our T, that's going to be P. We knew it was going to open downward. We had that from up above. So we had something that looked like that. And we just found our turning point. Our turning point here is 350.96. And then on our calculator, we could actually use the calculator to determine these points if we wanted to. So for letter C, it's saying use the 0 command on your calculator to determine to the nearest degree the two temperatures at which P equals 0, and label them on our graph drawn in part B. So using our 0 button, we can see these are going to be the two places where our p-value is going to equal 0, or the percentage popped is going to equal 0. So if we were to go back here and label this, this would be at 195, and this would be at 505. Okay, and keep in mind, if your percentage is 0, that's telling you if your temperature is at 195, you get 0 kernels, probably too cool. If it's at 505, probably way too hot, and you get 0 kernels popping. Okay, so for letter D, it's asking us if a typical batch of popcorn consists of 800 kernels, how many does the Crazy Caramel Corn Company expect to pop at the optimal temperature? Okay, well, optimal temperature, that's like your maximum. So what it's saying here is our maximum was 96%. I need to find that 96% of 800 kernels. So if we're going to find this, remember, convert 96 into a decimal, that's 0.96. And anytime you're saying that word of in math, it's a multiply. So 96% of 800, we're going to multiply those together. And that's going to get us about 768 kernels. So that's pretty good. And lastly here, for a batch of popcorn to be successful, the company wants at least 85% of its kernels to pop. So we have to write an inequality whose solution would represent all of the temperatures that would ensure a successful batch. And then we're going to solve the inequality graphically to the nearest degree. And we're going to show our graph labeling all of our relevant points. So if we're thinking about what that just said, we have the formula up above. So we're going to copy this formula down. Okay, so t squared plus 2.8t minus 394. Now it says it has to be at least, this has to be at least 85%. So it could be greater than 85%. It could also equal 85%. Remember, percent as a decimal would be 0.85. Okay, so it says we want to solve this graphically, solve this inequality graphically. So that means we're going to go to our calculator and we're going to use our calculator to help solve this. So on our calculator, we are going to want to enter in another equation. So I'm going to go up here and I'm going to put that other equation is 85. Remember, our p-value is representing our percent. Our percent here is 85. So I'm saying y equals 85. And that's what this line is. And you can see here, this is my equation, y equals 85. That's giving us an 85% rate. Okay, so now what we need to do, if I were to solve this, we need to figure out where these two graphs are going to intersect. So we can go back to our menu, analyze graph, and our intersection. Okay, so we go lower bound, upper bound. Here's one point of intersection. I'm going to do that again. And here's our second point of intersection. So if I were to look at this and answer this, we could say here, between and including 298 to 402 would be our answer to our degrees. And remember, these are representing degrees. So between 298 degrees and 402 degrees, that will give us a rate of return of our popping of 85%. So our inequality, I could say something like 295 would be less than or equal to t, which is less than or equal to 402. So this would be our inequality, our solution. And then it says we want to show it graphically. Well, I'm going to go back up here to our graph since we already have that done. What I'm going to do is add in that equation, y equals 85. So if this was, let's say, 85, keep in mind what we have. Right here, these are our 2 points of intersection that we found. And so the coordinate we had was 298, 85. And then over here, we had 402, 85. And so not only are these 2 points acceptable, but anywhere in here, anywhere in this range of our graph would be our solution. Okay, so here's just kind of applying some quadratics to real life situations where we would use them. Again, come to class with any questions and we'll practice some more of this. Hope you guys have a great day.